Fine, let's start. Number 10. The clocks in orbit. Right now, about 20,200 kilometers over your head, there is a small fleet of machines that have to lie about the time. They don't want to. They're built to be honest. Each GPS satellite carries an atomic clock, one of the most precise instruments humanity has ever made, the kind of clock that would lose maybe a second over millions of years. And before we launch one of these things, we do something that sounds insane. We deliberately set it wrong. We tune it to tick slow, on purpose, before it ever leaves the ground. Because we know something is going to happen to it up there. We know that the moment it reaches orbit, time is going to start running faster for that clock than it does for you. Here's why. Two different effects are fighting over that satellite, and they come from the same man, Albert Einstein, working two different problems. The first effect is speed. That satellite is not just sitting up there. It's tearing around the planet at roughly 14,000 kilometers per hour. And one of the strangest facts in all of physics is that the faster you move, the slower your time runs compared to someone standing still. So the satellite's speed alone drags its clock behind ours by about 7 microseconds every day. But there's a second effect, and it pushes the other way. Gravity also bends time. The stronger the gravity, the slower time crawls. Down here at the bottom of Earth's gravity, well, we're getting the brakes put on us. Up there, where gravity is weaker, time speeds up. And that effect is bigger, gaining the satellite about 45 microseconds a day. So you've got a clock losing 7 and gaining 45. Subtract 1 from the other, and the satellite's clock ends up running fast by about 38 microseconds every single day. Now, 38 microseconds sounds like nothing. It's 38 millionths of a second. You could not notice it if your life depended on it. But here's the thing. GPS works by timing radio signals to the nanosecond, and light travels about 30 centimeters in a nanosecond. So 38 microseconds of error is not a rounding problem. Left uncorrected, your position on the map would drift by about 10 kilometers per day. Think about that. If we had never accounted for Einstein, if we'd built GPS assuming time was just time everywhere, then within a couple of hours, your navigation would put you in the wrong neighborhood. By the end of the week, it would put you in the wrong city. Every plane landing, every ship, every little blue dot on every phone, all of it would slowly slide off the face of the earth. We fixed it by admitting the truth. Time is not the same up there as it is down here. And so every satellite gets its little pre-launch lie, tuned slow on the ground so that once it's flying through weaker gravity, it ticks at exactly the rate we need. Most people go their whole lives believing time is the one thing you can count on, the one fixed, neutral background that everything else happens against. And the machine in your pocket, the one that tells you where you are, only works because that belief is wrong. It's already broken. We just built around the cracks. Number 9. The clocks that flew around the world. Before we trusted satellites, somebody had to actually catch time bending. Not calculate it, not predict it. Catch it, red-handed, with a clock you could put in a seat and buckle in. That happened in October of 1971. Two scientists, Joseph Haffel and Richard Keating, did something that sounds more like a bar bet than an experiment. They took 4 cesium atomic clocks, the good ones, the expensive ones, and they bought them plane tickets, commercial flights, regular airline seats, and they flew those clocks around the entire world, once heading east, once heading west. The whole time, back home at the United States Naval Observatory, an identical set of clocks stayed on the ground, ticking away, minding their own business. Those were the control, the clocks that didn't travel. The idea was simple and a little audacious. Einstein said that motion and gravity both mess with time. So if you fly a clock and leave its twin at home, they should come back reading different times. Not because one of them broke. Because time itself would have passed differently for each of them. And that's exactly what happened. When the flying clocks came home and they compared them to the stay-at-home clocks, the numbers didn't match. On the eastward trip, the flying clocks had lost about 59 nanoseconds. On the westward trip, they'd gained about 273 nanoseconds. And those numbers lined up within the margins, with what relativity predicted before the planes ever left the ground. Now here's the detail that I love, the part that makes it feel almost mischievous. The direction mattered. East gave one answer. West gave the opposite. Why would time care which way you fly? Because the Earth itself is spinning, and when you fly east, you're flying in the same direction as that spin, adding your speed to the planets. When you fly west, you're going against it. So relative to the deeper frame, the whole system is moving through. An eastbound clock and a westbound clock are actually moving at different speeds. And different speeds mean different amounts of time. Sit with that for a second. These are two identical clocks. Same make, same model, built in the same lab, set to the same instant. They spend a day apart. One flies with the spin of the world and one against it. And when they're reunited, they no longer agree on how much time has passed. Neither one is broken. Neither one is lying. They just genuinely experienced different amounts of time. This is the famous twin paradox, the thought experiment, where one twin travels and comes home younger than the other. Except Hafele and Keating didn't do it with a thought experiment. They did it with luggage. They did it on scheduled airline flights, with clocks strapped into economy, cruising over the Atlantic. We tend to think of relativity as this exotic thing that only shows up near black holes or at the speed of light. Something that happens out there, in the extremes, far away from ordinary life. But it happened on a passenger jet. It happens every time you take off. Fly across the country, and you come home a few billionths of a second younger than you would have been. You will never feel it. But the clocks feel it. The clocks always feel it. Number 8. Your head is older than your feet. Okay. You don't need a plane. You don't need a satellite. You don't even need to leave the room. In 2010, a team at the National Institute of Standards and Technology in Boulder, Colorado, built a pair of the most precise clocks on the planet. These were aluminum-ion optical clocks, and they were sensitive to a degree that's honestly hard to describe. We're talking about a clock so stable, it would neither gain nor lose a second over billions of years. And when you have two clocks that absurdly precise, you can start asking questions nobody could ask before. Like, what happens if I take one of these clocks and lift it up? Just a little. Not to orbit. Not up a mountain. Just up. So that's what they did. They raised one clock by about 33 centimeters, roughly a foot, about the height difference between one shelf and the next, and the raised clock started ticking faster. Not metaphorically. Measurably. The clock that was 33 centimeters higher, sitting in very slightly weaker gravity, ran faster than the one below it. They could see it. They could put a number on it. Which means gravitational time dilation, this thing that we usually reserve for black holes and neutron stars, is happening across the height of a countertop. It's happening across the height of a person. Your head, right now, is a little further from the center of the Earth than your feet are. Which means your head is sitting in slightly weaker gravity. Which means, according to physics that has been tested to absurd precision, your head is aging faster than your feet. Now before you panic and start sleeping, standing up to even it out, let me give you the scale. Over a full lifetime, call it 79 years, the difference between your head and your feet adds up to about 90 billionths of a second. That's it. You will never win or lose anything you could measure. Your head and your feet will die at effectively the same age. But that's not the point. The point is that the effect is not zero. There is no height so small that time stops caring. Every step on a staircase is a slightly different rate of time. Every shelf in your house is running its own clock. The universe does not have one master clock ticking away in the background that everything shares. It has an infinite number of clocks, one at every single point in space, and every one of them is running at its own rate, depending on exactly how much gravity it's sitting in. And here's the part that quietly turns this from a curiosity into a tool. These clocks got so good that physicists realized you could run the logic backwards. If time runs slower lower down, then you can measure altitude just by measuring time. Put a clock somewhere, see how fast it ticks, and you can tell how high up it is without ever measuring the distance. They call it chronometric leveling. We are now so good at reading time that time has become a ruler. We used to think of time as the stage, the fixed floor everything stood on. Turns out the floor is tilted, everywhere, at every height, and we've just gotten precise enough to feel the slope under our own feet. Number 7. The particles that should be dead. There is a kind of particle falling through you right now that, by every rule of its own biology, should already be gone. It's called a muon. Think of it as the electron's heavier, short-lived cousin. And the key word there is short-lived. A muon has a half-life of about 2.2 microseconds. That's how long it takes for half of a batch of them to fall apart. They are, by nature, doomed almost the instant they exist. Here's where they come from. Out in deep space, cosmic rays, these are high-energy particles screaming across the galaxy, slam into the top of Earth's atmosphere. Those collisions, way up high, tens of kilometers overhead, create showers of muons. And those muons come racing down toward the ground at very nearly the speed of light. Now let's do the simple math, the naive way, the way that ignores Einstein. A muon lives about 2.2 microseconds. Even moving at nearly light speed, in that tiny sliver of time, it should only make it a few hundred meters before it decays. The muons are born tens of thousands of meters up. So by the time you get down to sea level, to a mountaintop, to your backyard, basically none of them should be left. They should all have died in the upper atmosphere, miles above your head. But they don't. They arrive in droves. In 1963, two physicists, David Frisch and James Smith, decided to actually go count them. They hauled a muon detector to the top of Mount Washington in New Hampshire, about 1,910 meters up, and they counted how many muons came through in an hour. The answer was about 563 per hour. Then they took the detector down to sea level and counted again. If muons died on the normal schedule, almost none should have survived the extra trip down the mountain. The count at the bottom should have been a tiny fraction of the count at the top. Instead, at sea level, they counted about 408 per hour, barely a drop. The muons were surviving a journey that by their own internal clock, they had no business surviving. Something was keeping them alive far longer than 2.2 microseconds should allow. That something was time dilation. The muons were moving so fast that, from our point of view on the ground, their internal clocks had nearly stopped. What felt like a normal, brief muon lifetime to the muon was stretched out, from our perspective, into something long enough to cross a mountain. The numbers gave a time dilation factor of about 8.8. From the muon's own point of view, that entire trip down through the atmosphere took roughly 1/9 of the time we measured. The mountain to the muon was basically 9 times thinner. And this is not some rare event in a fancy lab. This is happening constantly, everywhere, all the time. Muons are raining down on you right now. Several of them are passing through your body every second, and they are only reaching you at all because their experience of time and your experience of time have come apart. You are being gently rained on by particles that are, in a very real sense, living in slow motion. And the only reason they're here to touch you at all is that time, for them, is not the same time it is for you. Number 6. The day that isn't 24 hours. Here's a thing you were told as a kid that is quietly, technically, a lie. A day is 24 hours. The Earth spins once, and that's a day. Nice and even, the same, every time. It isn't. It never has been. And lately, it's getting weird enough that the people whose entire job is keeping time are genuinely worried. The length of a day, the actual time it takes the Earth to spin once, is not fixed. It wobbles. Earthquakes change it. The tides tug on it. Winds and ocean currents nudge it. The sloshing of the molten metal in Earth's outer core shifts it around. The planet is not a perfect clock. It's a spinning ball of rock and liquid and weather, and it speeds up and slows down by tiny amounts all the time. For most of human history, none of this mattered, because our clocks were worse than the Earth. But then we built atomic clocks. Clocks so steady, they don't care what the planet is doing. And suddenly we had two different definitions of time that didn't agree. There's atomic time, measured by the vibration of atoms, perfectly regular. And there's astronomical time, measured by the actual rotation of the Earth, messy and drifting. For decades, the Earth ran a little slow compared to the atomic clocks. So to keep the two in sync, timekeepers would occasionally add a second, a leap second. Between 1972 and 2016, they added 27 of them. Little patches, sewn in to let the sloppy Earth catch up to our perfect atomic time. But something changed. In the last few years, the Earth started spinning faster. It started setting records for the shortest days ever measured. And for the first time in history, we're facing the opposite problem. Instead of adding a second to wait for the Earth, we might have to subtract 1 to let our clocks catch up to the planet. They call it a negative leap second, and it has never been done. Not once. In 2024, a geophysicist named Duncan Agnew published a study in the journal Nature, projecting that we might need our first negative leap second around 2029. Now, here's the twist that really got me. One of the reasons the Earth's spin is a little confusing right now, one of the things partly holding the speed up back, is melting ice. As the ice at the poles melts, all that water spreads out toward the equator. And when mass moves away from the axis and out toward the middle, the planet spins a little slower, the same way a figure skater slows down by stretching their arms out wide. So the melting of the ice caps, driven by a warming climate, is measurably tugging on the length of the day. Agnew's work suggested that without that melting ice slowing things down, we'd have needed the negative leap second even earlier, around 2026 instead of 2029. Read that again. Human beings, by warming the planet and melting the ice, are altering how fast the Earth spins, which is altering global timekeeping, which is changing when we have to reach into the world's clocks and delete a second. And the timekeepers hate it, because so much of our technology assumes a second is a second, and time only ever moves forward. Adding a second is already a headache. Subtracting one, for the first time ever, could break systems that were never built to imagine time running backward, even for an instant. So the next time someone tells you a day is exactly 24 hours, you can smile and let it go. But you'll know, the day is a negotiation between the atoms and the oceans and the molten core and the melting ice. And the answer changes. Number 5, the early universe in slow motion. So far, everything we've talked about has been close to home. Satellites, planes, mountains, your own body. Let's go all the way out now. Let's look at the whole universe and ask whether time ran the same at the beginning as it does today. The answer, as far as we can see it, is no. And the way we found out is one of the more beautiful tricks in modern astronomy. Here's the setup. The universe is expanding. Space itself is stretching, carrying galaxies apart. And one of the strange consequences of that expansion is that it doesn't just stretch space. It stretches time. Or more precisely, it stretches our view of distant events, making things that happened far away and long ago appear to unfold in slow motion when their light finally reaches us. Einstein's picture of an expanding universe predicts this. If you could watch something happen in the very early cosmos, billions of years ago, you shouldn't just see it dimmer and redder. You should see it play out slower, like a film running at reduced speed. For a long time, we could confirm this using exploding stars, supernovae, at moderate distances. Their light curves, the way they brighten and fade, really did stretch out for more distant explosions, but people wanted to push it further, all the way back toward the beginning. The problem is that supernovae are one-time events, and the really distant ones are faint and rare. So in 2023, two astronomers, Geraint Lewis and Brendan Brewer, tried something clever. They used quasars as clocks. A quasar is a supermassive black hole at the heart of a young galaxy, gorging on matter and blazing brighter than the entire galaxy around it. And quasars flicker. They vary in brightness and patterns. Those patterns are messy, not a clean tick like a clock, but with enough quasars and enough patience, you can pull a kind of average rhythm out of them. Lewis and Brewer took a sample of about 190 quasars, observed over roughly 20 years by several sky surveys, reaching back to when the universe was very young, and they measured how fast those quasar clocks appeared to tick. Here's what they found. Looking back to when the universe was only about 1.5 billion years old, time appeared to be running about 5 times slower than it does today. 5 times. An event that would take 1 hour now, seen at that distance, seemed to smear out across 5 hours. Now, and this is crucial, the early universe was not actually in slow motion. If you had been there, right then, with a stopwatch, everything would have ticked along at a perfectly normal rate. Your watch would have looked fine. Your heartbeat would have felt normal. The slowdown isn't something that happened to the early universe. It's something that happens to our view of it, because all that light has been climbing across expanding space for 13.8 billion years to reach us, getting stretched the entire way. Which leads to a genuinely dizzying conclusion. How fast time is flowing is not a single fact about the universe. It depends on where you're standing and what you're looking at. From here, the dawn of the cosmos runs in slow motion. From there, it ran perfectly normally, and it would be us someday who looks slow. There is no master clock for the universe. There never was. There's just a web of observers, each one convinced their own time is the normal one, all watching everyone else run slow. Number 4. Time stops at the edge. We've been talking about time slowing down by tiny fractions, or by factors of a few. Now let's talk about the place where time slows down all the way, where it stops. A black hole. Gravity slows time. We've established that. GPS proves it. The NIST clocks prove it across a countertop. The stronger the gravity, the slower time crawls. So now imagine following that rule all the way down to the most extreme gravity that exists anywhere in the universe. The edge of a black hole. The event horizon. And here's what general relativity, Einstein's theory of gravity from over a century ago, tells you happens. Imagine you're watching a friend fall toward a black hole. A brave, doomed friend, drifting down toward that dark circle. From your safe distance, far away, you watch them fall. And as they get closer to the event horizon, you see their clock start to slow. Their movements start to drag. The light coming off them stretches out, reddens, dims, and they never arrive. From where you're standing, your friend slows, and slows, and slows, approaching the edge but never quite crossing it. They redden into invisibility, frozen at the boundary, hovering there. To you, the outside observer, it looks like they take an infinite amount of time to reach the horizon. Forever. You could wait longer than the age of the universe, and from your point of view, they'd still be there, stuck at the edge, moving slower and slower forever. Now here's the part that breaks your brain. Your friend does not experience any of that. From their point of view, nothing weird happens at the horizon. They don't slow down. They don't freeze. They fall right through it in a completely finite, ordinary amount of time on their own watch. A few minutes, maybe seconds. They cross the edge, and, at least in the simple picture, they don't even feel the exact moment they do it. There's no wall, no barrier, no click. They sail across the boundary and continue down toward whatever waits inside. So you have two observers. One says the crossing takes forever and never actually happens. The other says it took 8 seconds and is already over. And there is no experiment, no measurement, no view from above that settles who's right. They're both right. Time genuinely ran that differently for the two of them. This isn't science fiction, and it isn't a rounding error. This is the same effect that corrects your GPS, just cranked up to infinity, and you don't even need to fall in to feel a milder version. In the movie Interstellar, the crew lands on a planet orbiting close to a black hole, and 1 hour on that planet equals 7 years for the people waiting back on the ship. That scene was built on real general relativity, worked out by the physicist Kip Thorne. Get close enough to a black hole, and you really could step out after what felt like an afternoon and find that decades had passed for everyone you left behind. Everything we know about time assumes that we all share it, that there's a universal now ticking forward for everyone, everywhere, together. The black hole takes that assumption and tears it in half. Near enough gravity, one person's single heartbeat can outlast entire civilizations. A moment for one is an eternity for another. Time doesn't just bend at the edge of a black hole. It comes apart. Number 3, light lives in an eternal now. Let's talk about light. Because light does something with time that is so strange, we almost never say it out loud. We already know the rule. The faster you move, the slower your time runs. A muon moving near light speed barely ages. A satellite moving fast loses a few microseconds. So here's the obvious question, the one a curious kid asks and most adults never think about. What happens if you go all the way? What happens at the speed of light itself? The answer is that time stops completely. Not slows down. Stops. For something moving at the speed of light, no time passes at all. 0. Think about what that means for a beam of light crossing the universe. A photon leaves a distant galaxy, travels for billions of years across the cosmos, gets stretched by expanding space the whole way, and finally lands in your eye or in a telescope. From your perspective, that journey took billions of years. The photon is ancient. It's older than the Earth, older than the Sun. But from the photon's perspective, no time passed. The moment it was emitted and the moment it was absorbed, billions of years apart from where you sit, are, for the photon, the same instant. It was born and it died in the same breath. The entire journey across the observable universe, for the light itself, was instantaneous. Every star you have ever seen, every point of light in the night sky, sent that light on a journey that felt, to the light, like no journey at all. The light doesn't experience the crossing. It doesn't experience the wait. From the moment it leaves a star to the moment it hits your retina, from its own point of view, nothing happens in between. There is no in between. Now, physicists will correctly put an asterisk on this. Strictly speaking, you cannot climb aboard a photon. There is no valid frame of reference that moves at the speed of light, because the whole framework of relativity breaks down if you try to sit still relative to light. So, the photon's point of view is really the limit you approach as you get closer and closer to light speed, not a real chair you can sit in. But honestly, that asterisk makes it stranger, not tamer. Because it means the fastest thing in the universe, the thing that sets the ultimate speed limit, the messenger that carries every image and every signal we've ever received from the cosmos, has no experience of time whatsoever. For light, there is no past and no future. There is no duration. There is no and then. There is only a single, dimensionless now, stretched across the entire history of the universe. We measure our whole lives in the light of distant things. The sun that's 8 minutes old by the time it warms your face. The stars that are years or centuries or millennia old by the time you look up. And all of that light, every last photon, would tell you, if it could, that it left home and arrived at your eye in the very same instant. We live inside a slow story, told to us by messengers who feel no time at all. Number 2, antimatter, running backwards through time. Everything up to now has been about time slowing down or stopping. This one is different. This one is about direction, about which way time even goes. And it starts with the most ordinary particle in your body. The electron. For every kind of particle in the universe, there's an antiparticle, a mirror twin with the opposite charge. The electron's twin is called the positron. Same mass, opposite charge. When an electron meets a positron, they annihilate, both of them vanishing in a flash of energy. This is real. We make positrons in labs. There's a medical scan, the PET scan, the P stands for positron, that runs on this exact thing. Antimatter is not science fiction. It's Tuesday. But here's where it gets strange. Back in the late 1930s and 40s, two physicists, Ernst Stueckelberg and then, more famously, Richard Feynman, were working through the mathematics of these particles, and they noticed something buried in the equations. A positron, moving forward in time, is mathematically identical to an electron moving backward in time. Let me say that again, because it deserves it. You can describe antimatter perfectly, completely, with no contradictions, as ordinary matter running in reverse through time. In Feynman's picture, a positron just is an electron traveling backward through time. Take an electron, film it, run the film in reverse, and what you see, a particle with flipped charge moving the other way, is exactly a positron. Feynman built an entire, wildly successful theory of light and matter on this idea. When an electron and a positron meet and annihilate, you can read it as two particles destroying each other. Or you can read it as a single electron, traveling forward in time, that reaches a point, turns around, and heads back into the past as a positron. One particle. One zigzagging path through time. That description works. It gives the right answers. It's part of the machinery of the most precisely tested theory in the history of science. And this points at something deep and genuinely unsettling. When you look at the fundamental laws of physics, the equations that govern particles at the smallest scale, almost all of them work exactly the same, whether time runs forward or backward. The equations don't care. If you reversed the direction of time, the microscopic universe would obey the very same rules and look completely legal. Nothing in the basic laws says which way is forward. There's exactly one tiny exception. In certain rare particle decays, involving particles called kaons and B mesons, nature very faintly distinguishes between forward and backward. Experiments, including one called Babar, that reported a direct measurement in 2012, actually caught this asymmetry in the act. It is the only place in all of fundamental physics where the universe seems to know the difference between past and future. And it is astonishingly small. So step back and look at what that means. You feel time flowing, powerfully, undeniably, from past to present to future. It is maybe the most basic fact of being alive. And yet, when we look at the actual laws underneath everything, they almost don't contain that direction at all. The arrow of time you feel so strongly is barely written into the rules. It looks less like a law of the universe and more like an accident of how things happen to start. Every positron in every PET scan is, on one reading of our best physics, a little piece of matter briefly running the wrong way down the river of time. And the river itself, it turns out, might not have a current at all. Just a shape it happened to fall into. Number 1. When cause and effect lose their order. We've watched time slow down. We've watched it stop. We've watched its direction nearly dissolve. For the last one, we're going to take away the thing you thought was the most solid, the most obvious, the most unbreakable part of time. The order things happen in. Cause and then effect. First this, then that. You would bet your life on it. You strike the match, then it lights. Never the other way around. The whole idea of time is really just this. One thing after another, in a definite order. A cause is B. That's the bedrock. That's the floor beneath the floor. Quantum mechanics just pulled it up. Here's the idea. In the quantum world, things can exist in what's called superposition. A particle doesn't have to be here or there. It can be in a blur of both at once until you look. We usually apply this to position or spin, but some physicists asked a wild question. What if you could put the order of events into superposition? What if you could arrange things so that A happens before B and B happens before A are both true at the same time? They call it indefinite causal order, and the machine they dreamed up to do it is called the quantum switch. Here's roughly how it works. You take a single photon and you send it through two operations. Call them A and B. In an ordinary world, it has to be one order or the other. Either the photon goes through A first and then B, or it goes through B first and then A. Pick one. But in the quantum switch, the photon's path is controlled by another quantum bit that is itself in superposition. So the photon travels a route where A comes before B, and at the very same time, a route where B comes before A. Not one, then we're unsure which. Both. Genuinely both. Layered over each other, with no fact of the matter about which operation actually came first. And in 2017, and in a string of experiments after that, physicists actually built this. In the lab. With real photons on real optical tables. And then they had to prove that it wasn't a trick, that the photon wasn't secretly picking one order and hiding it. So they designed a measurement called a causal witness, a test that can only come out a certain way if there is no definite order. Some of these experiments confirmed indefinite causal order by something like 18 standard deviations. In physics, that is not a maybe. That is a wall. That is nature flatly telling you there was no fact about which came first. Think about how deep that cuts. It's one thing for time to run slow or stop or blur its direction. But this is saying that the sequence itself, the before and after, the very order of cause and effect, is not always a fixed feature of reality. Under the right quantum conditions, it becomes fuzzy, negotiable, undefined, which raises the possibility that haunts the edge of modern physics. Maybe the smooth, ordered flow of time, the one thing after another that feels so absolute, isn't fundamental at all. Maybe it isn't built into the universe at the deepest level. Maybe it's something that emerges later on top of a reality that underneath doesn't have a strict order of events. Maybe before and after is not the foundation of the world. Maybe it's something the universe assembles, a story stitched together after the fact, out of a layer where the ordering simply wasn't there yet. We started this whole journey with a clock in orbit, told to lie by 38 microseconds a day. That felt like a small crack, a rounding error in something we thought was solid, But follow the crack all the way down, and you arrive here, at a photon on a lab bench in a city on Earth, quietly refusing to say what happened first. Everything we know about time, the rate it runs, the direction it flows, the order things happen in, turns out to be softer than it feels. Not fixed, not universal, not the neutral stage we thought everything was standing on. Time is not the floor of reality. It might be one of the things reality is still, right now, in every experiment, in every falling muon, and every frozen edge, and every photon that feels no journey at all, quietly making up as it goes. And maybe that's the strangest thought of all. Not that our clocks are wrong, but that time, the thing we trust more than anything, the thing we build our entire lives around, may be the universe's most convincing illusion. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.